Picture for a moment something magnificent, a spinning pulsar rhythmically flashing like a cosmic lighthouse, or a spiral galaxy slowly turning its grand, star-filled arms in the velvet darkness of space. What you're seeing is breathtaking, but the true magic lies in what you can't see: an invisible force that guides those stars, protects entire worlds, and carves the very fabric of the cosmos. That force is magnetic fields, and it's one of the universe's quietest but most powerful architects. It shapes everything from the birth of stars to the paths of comets, and today, we're setting out on a journey to explore 30 incredible ways this hidden force molds the universe as we know it. You're about to discover how magnetic fields act like silent conductors in the grand orchestra of the cosmos, directing the flow of cosmic gas, energizing particles to nearly the speed of light, and even sheltering planets like our own Earth from the sun's furious outbursts. These fields are everywhere, threading through galaxies, woven into nebulae, even embedded in the simplest atoms. Yet despite their invisibility, their influence is written across the night sky in the shimmer of auroras, the structure of galaxies, and the slow dance of planets. This isn't just science, it's a story written in forces and fields, a narrative of attraction and repulsion that has, since the beginning of time, shaped reality itself. So settle in, open your mind to wonder, and get ready to see the universe in a whole new light. Over the course of this video, we'll travel from the smallest scales to the largest structures imaginable, uncovering how magnetic fields not only build worlds but also guard them, energize them, and connect them across impossible distances. This is a journey into one of nature's most elegant and essential tools, one that works silently, constantly, and beautifully behind the scenes of everything that exists. Let's begin. Deep within the sun's fiery core, a powerful engine is constantly at work. This is the solar dynamo, the fundamental process that generates the star's immense magnetic field. It begins with the churning motion of superheated plasma, a sea of charged particles that rises, cools, and sinks in a continuous convective loop, combined with the sun's differential rotation, where the equator spins faster than the poles. This flowing, conductive material gets stretched and twisted, effectively acting like a gigantic electrical generator. This motion transforms kinetic energy into magnetic energy, weaving a complex, planet-sized magnetic field from the chaos. This process isn't steady and calm, it's cyclical and dynamic, leading to what we observe as the solar cycle. Approximately every 11 years, the sun's magnetic field completely flips polarity, building from a period of minimal activity to a dramatic maximum and back down again. The most visible signs of this cycle are sunspots. These darker, cooler patches on the sun's surface are not blemishes but rather knots of intense magnetic activity, places where the magnetic field is so strong it suppresses the convection of heat, making those areas appear darker against the brighter surrounding photosphere. The number of sunspots we see waxes and wanes in a direct reflection of the magnetic turmoil within. This rhythmic magnetic heartbeat is the primary driver of all space weather throughout our solar system. During solar maximum, the sun is prone to massive eruptions, solar flares and coronal mass ejections, which are essentially enormous releases of magnetic energy. These events hurl radiation and charged particles across the solar system at incredible speeds. When this solar wind, laden with the sun's magnetic influence, washes over Earth, it interacts with our planet's own magnetic field, creating the beautiful auroras near the poles. But it can also pose serious risks, potentially disrupting satellites, interfering with power grids, and affecting communications. So the sun's magnetic field, born from its deep internal dynamo, doesn't just define the star itself. It reaches out across millions of miles to touch every planet and craft that orbits it. Now, if that churning solar dynamo is the engine, then solar flares and coronal mass ejections are its most spectacular and violent backfires. These are the cosmic equivalent of magnetic storms, explosive events born from a simple yet powerful principle. When you twist a magnetic field too far, it will eventually snap. High above the sun's surface, in its scorching outer atmosphere known as the corona, magnetic field lines are constantly being stretched, wound and stressed by the motion of the plasma below, much like winding up a rubber band. These lines of magnetic force become tangled and kinked, storing a colossal amount of pent-up energy. The trigger for the explosion is a process called magnetic reconnection. Think of it like this. You have two powerful magnets, their opposing poles held dangerously close together. They're pushing against each other, building tension, until the system can no longer sustain that strain. In an instant, the magnetic field lines break and then rapidly reconnect in a new, lower energy configuration. It's this sudden rearrangement that unleashes all the stored energy in two primary ways. The first is a solar flare, an intense flash of radiation that erupts across the electromagnetic spectrum. This isn't just a burst of light. It's a catastrophic release of energy equivalent to millions of hydrogen bombs exploding simultaneously. This flash of X-rays and ultraviolet radiation can reach Earth at the speed of light, immediately disrupting our planet's ionosphere and affecting radio communications. But the Sun can unleash an even more massive eruption, the coronal mass ejection, or CME. This is where the Sun doesn't just flash with light, it literally throws a piece of itself into space. During a powerful reconnection event, billions of tons of superheated plasma, a seething cloud of protons and electrons, are ripped from the Sun's corona and hurled outward, trapped within its own magnetic prison. This colossal bubble of magnetized gas can travel through the solar system at speeds of millions of miles per hour. While the light from a flare arrives at Earth in just over 8 minutes, a CME takes its time, traveling for 1 to 3 days before it might collide with our planet's magnetic field. When it does, that's when the real celestial fireworks begin, compressing our magnetosphere and sparking intense geomagnetic storms that paint our skies with auroras, but also threaten the technological backbone of our modern world. While the Sun's magnetic fury can unleash disruptive storms, that very same force also provides our solar system with an extraordinary form of protection, shaping a safe haven on a truly galactic scale. This brings us to the heliosphere, a colossal magnetic bubble that encases every planet, every comet, and every bit of dust that calls our solar system home. It's a shield forged by the Sun itself, and it is our first and most important line of defense against the harsh realities of interstellar space. This immense structure is created by the solar wind, that constant stream of charged particles and magnetic field that flows outward from the Sun in all directions. Think of it as the Sun constantly exhaling a magnetized breath. As this wind races outward at supersonic speeds, it pushes against the thin gas and dust that floats in the voids between stars, known as the interstellar medium. Eventually, the pressure of the solar wind pushing out balances with the pressure of the interstellar medium pushing in. This balance point, this boundary where the Sun's influence finally ends and true interstellar space begins, is the outer edge of the heliosphere. It's not a perfect sphere by any way. As our solar system moves through the galaxy, this bubble is shaped into something more like a vast cosmic parachute, with a rounded nose in the direction we're traveling and a long, stretched tail flowing out behind us. Inside this protective magnetic cocoon, we are sheltered from a relentless and invisible rain known as galactic cosmic rays. These are not rays of light, but are instead highly energetic, fast-moving atomic nuclei, mostly protons, that are accelerated to nearly the speed of light by distant supernova explosions and other violent events across the Milky Way. These particles are so energetic that they can penetrate solid matter, and for any living organism, prolonged and unprotected exposure would be devastating, damaging cells and DNA. The heliosphere's magnetic field acts as a powerful deflector shield. bending the paths of these incoming charged particles and significantly reducing the amount that can reach the inner solar system. Without this bubble, the background radiation level on Earth would be immensely higher, making the emergence and evolution of complex life as we know it far more difficult, if not impossible. So, the next time you feel the sun's warmth on your skin, remember that its invisible magnetic influence extends far beyond the light you see, crafting a safe zone that has, for billions of years, quietly nurtured and protected the delicate experiment of life on our world. But that solar wind, the very same force that carves out our protective heliosphere, is also a constant and relentless threat. It's a supersonic river of charged particles, and if it were to strike Earth's atmosphere directly, it would slowly but surely erode it away, stripping our air into the void of space and leaving our planet a barren, lifeless rock. So how do we survive? The answer lies in a remarkable, invisible structure that our own planet generates, the magnetosphere. Think of it as Earth's personal force field, a dynamic, teardrop-shaped bubble of magnetic influence that stands permanently between us and the fury of the sun. This incredible shield originates from a powerful engine deep within the Earth itself, a spinning, churning ocean of molten iron and nickel in the outer core. This motion, driven by the heat left over from the planet's formation and the radioactive decay of elements deep below, acts as a colossal dynamo. Just as moving a wire through a magnetic field can generate an electric current, the convective motion of this liquid metal generates and sustains our planet's global magnetic field. This field extends far out into space, creating a protective cavity that the solar wind must flow around, not through. When that million-mile-per-hour wind of charged particles slams into Earth's magnetic field, something extraordinary happens. The magnetosphere acts like a rock in a stream, diverting the flow of the solar wind around our planet. Most of these particles are deflected harmlessly into the depths of the solar system. But the shield is not a perfect, impenetrable barrier. It's a dynamic and interactive system. Some of the solar wind's energy and particles become trapped by the magnetic field lines, funneling them down towards the planet's north and south magnetic poles. As these high-energy particles collide with oxygen and nitrogen atoms in our upper atmosphere, they transfer their energy, causing those atoms to glow in the spectacular, shimmering curtains of light we know as the aurora borealis and aurora australis. The auroras are not just a beautiful side effect. They are a visible sign of our atmosphere being protected, a release of that captured solar energy in a safe and breathtaking display. This shielding is absolutely vital for life. Beyond creating the northern and southern lights, the magnetosphere's primary job is to prevent the solar wind from directly impacting our atmosphere. Without it, the relentless bombardment would act like a cosmic sandblaster, gradually ripping away the gases that make up our air and our protection from ultraviolet radiation. We only need to look at our neighboring planet Mars to see a tragic example of a world that lost this protection. Billions of years ago, Mars is thought to have had a global magnetic field and a much thicker, warmer atmosphere, possibly even with liquid water on its surface. But when its core cooled and its dynamo shut down, its magnetosphere faded away. Left exposed, the solar wind systematically stripped away most of the Martian atmosphere, leaving it the cold, desolate desert we see today. Earth's persistent magnetic heart, therefore, is more than just a geological curiosity. It is the silent guardian of every breath we take, the unsung hero that has preserved the delicate conditions necessary for life to not just begin, but to thrive and evolve for billions of years. This journey of a single solar particle, from a violent eruption on the sun to a fleeting flash of light in our polar skies, is one of the most stunning examples of our planet's interconnectedness with the cosmos. It begins with a solar event, a flare or a coronal mass ejection, that hurls a cloud of charged particles, primarily electrons and protons, in our direction. Traveling across the 93 million-mile gulf of space, This solar wind is the raw material, the paint for the celestial canvas, but it needs a brush and a guide to create its masterpiece, and that guide is Earth's magnetosphere. As this stream of charged particles approaches our planet, it doesn't hit a solid wall. Instead, it encounters the invisible lines of force that make up our magnetic field. For the most part, this field acts as a deflector, pushing the solar wind around the edges of the magnetosphere. But the field is weakest at the poles, and it's here that the magic happens. The geometry of Earth's magnetic field creates two funnel-like regions above the north and south poles, known as the polar cusps. It is through these magnetic portals that particles from the solar wind can slip inside our protective shield. Once trapped within the magnetosphere, these particles are accelerated and channeled downward, spiraling along the magnetic field lines like trains on invisible tracks, hurtling toward the upper atmosphere over the Arctic and Antarctic circles. The final, brilliant act of this long journey is a collision. As these high-energy particles slam into the thin air 60 to 200 miles above the Earth's surface, they transfer their energy to the atoms and molecules of our atmosphere, primarily oxygen and nitrogen. Much like charging a battery, this influx of energy excites these gas particles, pushing their electrons into higher energy states. But nature seeks balance, and almost instantly, these excited electrons snap back to their normal, resting state. To shed that excess energy they've absorbed, they release it in the form of a tiny packet of light, a photon. The specific color of this light depends entirely on which gas is being excited and the altitude of the collision. The most common auroral glow, a haunting, shimmering green, comes from oxygen atoms roughly 60 miles up. At higher altitudes, where the atmosphere is even thinner, collisions with oxygen can produce a much rarer, deep red hue. Meanwhile, interactions with nitrogen molecules can generate brilliant bands of pink, magenta, and even a deep blue-purple, often seen at the lower edges of the most vibrant displays. The shape of the aurora, those graceful, dancing curtains of light, is a direct map of the magnetic field lines themselves, revealing the architecture of the very force that guides the particles there. It is a light show written in the language of physics, a mesmerizing demonstration of how our planet's invisible magnetic forces transform a potentially destructive solar storm into one of the most beautiful phenomena on Earth. While Earth's magnetosphere is our life-preserving shield, it is a modest structure compared to the true titan of our solar system. Journey outward past the asteroid belt, and you enter the domain of a magnetic king Jupiter. The gas giant's magnetosphere is not merely large. It is the single largest structure in our entire solar system, a colossal bubble of magnetic influence so vast that if it were visible to the naked eye, it would appear larger than the full moon in our night sky. In fact, this immense magnetic cavity is so gigantic that it could easily contain the Sun itself, with room to spare. This is the realm of a planetary magnetic field so powerful it defies earthly comparison. The engine behind this phenomenal force lies deep within Jupiter's enigmatic interior. Unlike Earth, Jupiter has no solid iron core to act as a conventional dynamo. Instead, its magnetic field is generated by a vast, swirling ocean of metallic hydrogen. Under the immense pressure of the planet's crushing gravity, the hydrogen that makes up most of Jupiter's bulk is compressed into a bizarre, liquid metallic form. This substance behaves like a flowing superconductor of electricity. The planet's incredibly rapid rotation, spinning once on its axis every 10 hours, churns this seething, metallic sea, generating powerful electric currents that, in turn, produce a magnetic field of almost unimaginable strength. This field is nearly 20,000 times more powerful than Earth's, a testament to the furious dynamo raging within the gas giant. This awesome magnetic power carves out a domain of extreme and violent beauty. Jupiter's magnetosphere acts as a colossal particle trap, snatching charged materials from the solar wind and, more importantly, from the planet's own volcanic moon, Io. Io's constant, violent eruptions spew vast amounts of sulfur and oxygen into space, which become ionized and are immediately captured by Jupiter's gravitational and magnetic grasp. These particles are then accelerated to nearly the speed of light, forced to spiral along the giant's magnetic field lines and creating donut-shaped regions of intense radiation around the planet known as radiation belts. The energy within these zones is so intensely lethal that it would instantly fry the electronics of any spacecraft daring to pass through. The influence of this magnetic kingdom is written across the Jovian system in brilliant and dramatic ways. The same process that creates Earth's gentle auroras produces Jupiter's polar light shows, but on a monstrous scale. The planet's auroras are permanent, raging hurricanes of light, hundreds of times more energetic than our own, glowing in brilliant ultraviolet and X-ray frequencies. They are powered by the relentless influx of particles and by the powerful electric currents generated as Jupiter's magnetic field sweeps past the magnetic fields of its large moons. This continuous, dynamic interaction between the planet and its satellites illustrates a profound truth. A magnetosphere is not an isolated shield. It is an active, living system that governs the environment of an entire planetary family, accelerating particles, fueling immense auroras, and dictating the rules of existence for every world within its overwhelming magnetic embrace. Yet for all its immense power, Jupiter's magnetic field is a tilted, off-kilter giant, its axis leaning away from the planet's spin by about 10 degrees, a feature we see on many worlds, including our own. This makes the magnetic field of its ringed neighbor, Saturn, a profound cosmic oddity. When the Voyager probes first measured it, scientists were met with a finding so unexpected, it seemed to defy the known rules of planetary physics. Unlike every other planet we've studied, Saturn's magnetic field is almost perfectly aligned. Its magnetic north and south poles are nearly indistinguishable from its geographic poles, with a tilt of less than a single degree from its axis of rotation. It is a magnetic field of almost perfect symmetry, a precise and orderly exception in a universe of chaotic and tilted dynamos. This remarkable alignment presents a fascinating puzzle. A planetary magnetic field is born from chaos from the churning, turbulent motion of conductive fluids deep inside a planet. This dynamo process is inherently messy, and that internal turmoil usually expresses itself as a magnetic field that is offset or tilted. Earth's magnetic north, for instance, is hundreds of miles away from its geographic North Pole. For Saturn's field to be so perfectly centered, something must be suppressing that natural turbulence, acting as a stabilizing force on the magnetic heart of the planet. The leading theory points to a breathtaking internal phenomenon, helium rain. Deep within Saturn, under immense pressures and temperatures, hydrogen exists in that same liquid metallic form as it does on Jupiter. But Saturn is less massive, meaning the pressures in its outer core are just on the edge of what's needed to keep helium dissolved within that metallic hydrogen soup. As this fluid mixture rises and begins to cool, the helium can no longer stay in solution. It is thought to condense into droplets and fall inward toward the planet's center like a slow, steady rain. This continuous precipitation of helium does two critical things. First, it releases gravitational energy, which helps explain why Saturn emits more heat than it receives from the Sun. Second, and more importantly for its magnetic field, this falling rain may be stabilizing the dynamo itself. The region where this helium rain occurs could be acting as a stable, layered shell around the inner dynamo. This layer would effectively filter out the more chaotic convective motions, allowing only the most organized, symmetric flows to influence the magnetic field generated deeper within. It's like placing a steadying hand on a wobbly top. The internal chaos is still there, but its expression is smoothed into perfect order. This process would result in the uniquely symmetric dipole field we observe, a quiet magnetic hum emanating from a world with a surprisingly stable interior. This perfect alignment has a fascinating and visible consequence. Because the field is so symmetrical, the auroras on Saturn, while still immense and powerful, tend to form almost perfect rings around its poles. Without a significant tilt to warp and distort them, these brilliant halos of light crown the planet with a consistency and order not seen anywhere else. Saturn's mysterious magnetic field is more than just a curiosity. It is a celestial clue. By studying its unique symmetry, we are given a rare window into the hidden processes shaping the deep interior of a gas giant, revealing a world where it literally rains liquid helium, quietly sculpting one of the most perfectly ordered magnetic fields in the solar system. Our story now turns to a world that serves as a sobering cautionary tale, a stark reminder that a magnetic field is not a permanent guarantee. Mars, our rust-colored neighbor, was not always the cold, arid desert we see today. Billions of years ago, it was a profoundly different place. Orbital photographs from our spacecraft reveal unmistakable evidence: the ghostly outlines of vast river deltas, deep channels carved by catastrophic floods, and lakebeds that once held standing water. This ancient Mars was a world with a thicker atmosphere, warmer temperatures, and liquid water flowing freely across its surface, conditions that, at least theoretically, could have provided a foothold for the emergence of life. But something catastrophic happened. That world vanished, and the key to its transformation lies in the story of a protective shield that simply faded away. The prevailing theory, supported by data from orbiters and rovers, is that early Mars was much more geologically active than it is today. Like Earth, it is thought to have possessed a molten, churning metallic core, a planetary dynamo that generated a global magnetic field. This magnetic shield would have acted exactly like Earth's, deflecting the relentless onslaught of the solar wind and sheltering the Martian atmosphere from direct erosion. Under this protection, the planet was able to maintain the atmospheric pressure necessary to keep water in its liquid state on the surface, allowing for rivers to flow and lakes to pool. For perhaps a billion years, Mars was a wet world, a second blue planet in the inner solar system. But Mars is a smaller world than Earth, with only about half the diameter and a little over a tenth of the mass. This smaller size was its ultimate undoing. A smaller planet loses its internal heat much more rapidly. Without the insulating bulk of a larger world, the fiery engine at the core of Mars began to cool. The convective churning of its liquid metal core gradually slowed, sputtered, and eventually ceased. The dynamo effect shut down, and with it, the planet's global magnetic field faded into silence. The invisible force field that had guarded the Martian atmosphere for eons simply vanished, leaving the planet completely exposed and vulnerable to the full fury of the sun. The consequences were slow, relentless, and utterly devastating. Without a magnetosphere to stand in its way, the high-energy particles of the solar wind struck the upper atmosphere of Mars directly. This process, known as sputtering, acts like a cosmic sandblaster. The incoming particles transfer their energy to the atmospheric molecules, oxygen, carbon dioxide, water vapor, giving them enough velocity to escape Mars's relatively weak gravity. Molecule by molecule, the atmosphere was systematically stripped away and blown off into interplanetary space. NASA's MAVEN orbiter has directly measured this ongoing atmospheric loss, confirming that the process is most intense during solar storms when the sun's fury is at its peak. Over hundreds of millions of years, this relentless erosion transformed the planet. As the atmospheric pressure plummeted, any remaining liquid water on the surface instantly became unstable. It could no longer exist as a liquid. It either flash froze into ice or sublimated directly into vapor, only to be subsequently broken apart by solar radiation and lost to space as well. The planet's surface temperature dropped dramatically without an atmosphere to provide a greenhouse effect. The winds died down, the rivers dried up, and the once dynamic world became a frozen, desiccated husk. The only water that remains is locked away in polar ice caps or hidden deep underground. The story of Mars is a tragic one of a world that lost its shield, and in doing so, lost its world. It stands as a powerful testament to the fact that a planet's magnetic heart is not just a geological feature. It is the guardian of its very potential, the protector of its atmosphere, and ultimately, the keeper of its future. Just when we thought we understood the rules, the solar system presents us with a delightful and head-scratching exception. After the tragic story of Mars, a world that lost its magnetic shield, we arrive at Mercury. This small, sun-scorched world should, by all conventional wisdom, be completely and utterly magnetic dead. It's the smallest planet in our solar system, not much larger than our own moon. A world that small should have cooled down and solidified completely billions of years ago. Its internal dynamo long since frozen into stillness. And yet, when NASA Mariner 10 spacecraft flew by in the 1970s, it detected something utterly unexpected: the faint, unmistakable whisper of a global magnetic field. It was a discovery that forced scientists to completely rethink their models of how planetary magnetism works. The sheer existence of this field is the central puzzle. A magnetic dynamo requires three key ingredients: a conductive fluid, motion within that fluid, and rotation. For a planet as tiny as Mercury, the first ingredient was supposed to be impossible to find. Its core, relative to the planet itself, is enormous, making up about 85% of its radius. That's a massive ball of iron. The thinking was that in such a small body, this immense core should have radiated its heat away into space and solidified completely eons ago, turning into a single, solid sphere of iron with no liquid left to churn and generate a magnetic field. A solid core cannot convect. It's a geological statue, incapable of powering a planetary dynamo. Mercury, it seemed, was breaking the fundamental rules of planetary physics. So how does it do it? The leading theory today is one of fascinating complexity, suggesting that Mercury's core is not a simple, solid ball, but is instead an intricate layered structure, a kind of cosmic onion with a surprising secret at its heart. The current model proposes that Mercury's core is partially molten. Imagine it like this: at the very center of the planet, there is a solid inner core made of iron, but surrounding that is a deep, slushy layer of liquid iron mixed with lighter elements like sulfur. This outer shell remains liquid because the sulfur acts like an antifreeze, dramatically lowering the melting point of the iron alloy and preventing it from solidifying even as the planet continues to cool. But a liquid layer alone isn't enough to create a dynamo. That liquid needs to move. This is where another of Mercury's peculiarities comes into play: its incredibly eccentric orbit. The planet doesn't travel around the Sun in a neat circle. It follows a stretched, elliptical path that brings it dramatically close to the Sun, and then swings it far away. This wild orbital ride, combined with the gravitational tug of war between the Sun and Mercury itself, creates intense tidal forces that squeeze and flex the entire planet. This constant tidal pummeling is thought to stir that slushy outer core, providing the necessary motion to generate electrical currents and power a weak, but global, magnetic field. This faint field, though only about 1% the strength of Earth's, is far from insignificant. It's just powerful enough to stand up to the ferocious solar wind, carving out a small, teardrop-shaped magnetosphere around the planet. This miniature shield is constantly being compressed by the sheer force of the Sun's proximity, but it persists, diverting some of the solar wind and creating a small, protected zone. The Messenger orbiter provided stunning confirmation of this, mapping the field and even observing signs of magnetic reconnection events, miniature versions of the solar storms that rack our own Sun. Mercury's tenacious little field is a brilliant reminder that nature is always more inventive than our textbooks. It proves that even the smallest, most unlikely worlds can cling to their magnetic identity, harnessing unique and unexpected mechanisms to project a faint whisper of order against the chaos of the cosmos. Now we come to a world that is, in many ways, Earth's twisted sister. A planet that shows us a terrifying alternate reality of what our own home could have become. Venus is almost identical to Earth in size, mass, and composition, and it formed at a similar distance from the Sun. Yet its surface is a crushing, acid-soaked hellscape with temperatures hot enough to melt lead, all shrouded under a thick, suffocating blanket of carbon dioxide. While many factors led to this inferno, one critical difference lies in a fundamental absence. Venus has no global magnetic field to call its own. This missing shield is not just a side note. It is a key player in the planet's tragic story, deeply intertwined with the nightmare conditions that exist there today. So why does Venus, a near twin of Earth, lack this protective barrier? The leading suspect is its painfully slow rotation. A day on Venus, the time it takes to complete one full spin on its axis, is longer than its entire year. It takes 243 Earth days to rotate just once, and it does so backwards compared to most other planets. This sluggish spin is likely the death knell for a global dynamo. For a magnetic field to generate itself through the dynamo effect, the churning motion of a conductive fluid in the core needs to be organized and sustained by the Coriolis force, the same effect that creates hurricanes and ocean currents on Earth. This force is weak on a slowly rotating world. Without that rapid spin to stir the pot and create the necessary turbulence, the convective currents in Venus's core may be too disorganized and lethargic to generate a planet-spanning magnetic field. The engine, for all intents and purposes, has seized up. This leaves Venus completely exposed. Without its own global magnetic shield, the full force of the solar wind slams directly into the planet's upper atmosphere. But the story isn't quite as simple as the solar wind simply blowing the atmosphere away, as it did with Mars. Venus has an incredibly thick and massive atmosphere, creating a surface pressure 92 times greater than Earth's. This sheer weight provides a form of passive resistance against erosion. The interaction is far more complex and insidious. The solar wind, with its own embedded magnetic field, doesn't hit a solid barrier, but instead interacts with the planet's ionosphere, a layer of the atmosphere where gases are ionized by solar radiation. This interaction creates a fascinating and unique structure known as an induced magnetosphere. As the solar wind and its magnetic field press against Venus's ionosphere, they don't just deflect around it. Instead, the moving magnetic field lines from the Sun drape themselves over the planet, stretching and folding around it. This process induces electrical currents in the ionosphere, and those currents, in turn, generate a weak, localized magnetic field that bulges out on the Sun-facing side and stretches into a long, comet-like tail on the night side. It's a magnetic field that is not born from within the planet, but is rather a reaction to external assault, a ghostly echo of the Sun's own power. This induced magnetosphere does provide some buffering, but it is a flimsy and porous defense compared to Earth's robust global shield. The true danger of this direct interaction is not a rapid stripping away of the entire atmosphere, but a slow, chemical dismantling that fuels the runaway greenhouse effect. The solar wind provides a constant source of energy that breaks apart molecules in the upper atmosphere, particularly water vapor. When high-energy solar particles split water molecules, the lightweight hydrogen released from the heavier oxygen can easily escape Venus's gravity and drift off into space. Over billions of years, this process is thought to have been a major contributor to Venus losing virtually all of its ancient water. Without vast oceans to absorb carbon dioxide, the gas built up relentlessly in the atmosphere from volcanic outgassing, creating the incredible greenhouse oven we see today. The solar-wind interaction doesn't just remove water. It also helps create the planet's infamous clouds of sulfuric acid. Solar radiation and particles break down sulfur dioxide and other compounds in the upper atmosphere, leading to chemical reactions that form sulfuric acid droplets. These highly reflective clouds perpetually shroud the planet, trapping heat below and contributing to the hellish surface temperatures. So, while Venus's lack of a magnetic dynamo didn't single-handedly create its inferno, it set in motion a chain of atmospheric chemical processes that robbed the planet of its water and helped lock in the conditions for a permanent, suffocating greenhouse. It stands as a powerful cosmic lesson. A magnetic field is more than just a shield against particles. It is a guardian of a planet's entire atmospheric chemistry, and without it, a world can slowly, irrevocably cook itself. While our own moon is a silent, geologically dead companion, one of Jupiter's many satellites tells a far more dynamic and surprising story. Meet Ganymede, not just the largest moon in our solar system, but a world larger than the planet Mercury. It's a colossal sphere of rock and ice, but it holds a secret that sets it apart from every other moon. It possesses its very own, internally generated magnetic field. This makes Ganymede a true cosmic anomaly, a moon that behaves like a planet, generating a protective magnetic shield from deep within its own core. This remarkable field is the signature of a world that is still hot and active on the inside. The leading explanation points to a process we've seen in planets, a dynamo effect. Scientists believe that deep within Ganymede's layered interior, there lies a core of molten, liquid iron. The heat left over from the moon's formation billions of years ago, combined with the intense gravitational squeezing it receives from its orbital dance with Jupiter and the other large moons, keeps this core churning. This convective motion of the conductive liquid metal acts as a powerful generator, creating a global magnetic field that blossoms out into the space around Ganymede. But this isn't a simple, standalone field. Ganymede's magnetosphere exists in a state of constant, dramatic negotiation with the overpowering influence of its parent planet. It is a tiny magnetic bubble, a delicate structure completely immersed within Jupiter's colossal, stormy magnetosphere. As Ganymede orbits Jupiter, it continuously plows through the giant's rotating magnetic field and the dense plasma trapped within it. The result is a breathtaking and complex magnetic dance. Ganymede's intrinsic field carves out its own protected cavity, a pocket of relative calm within the raging particle storms of the Jovian system. This creates a unique two-layered magnetic environment, with field lines from both the moon and the planet connecting and interacting in a constantly shifting architectural wonder. This intrinsic magnetic field does far more than just create a fascinating celestial interaction. It plays the most crucial role of all, that of a guardian. Data from spacecraft like Galileo strongly suggest that Ganymede harbors a vast, global ocean of salty liquid water, hidden beneath a thick, icy crust. This ocean is believed to hold more water than all of Earth's oceans combined, making it one of the most promising places in our solar system to look for environments suitable for life. But such an ocean would be incredibly vulnerable without protection. The intense radiation from Jupiter's belts, a hail of high-energy electrons and ions, would constantly bombard the moon's surface, and that radiation could penetrate the ice, sterilizing the waters below and breaking apart any complex organic molecules that might form. Ganymede's self-generated magnetic field acts as a vital deflector, shield against this onslaught. It stands between the moon's interior and the hostile space environment, diverting the most dangerous particles away from the surface and especially from the polar regions. By creating this protected zone, the magnetic field drastically reduces the radiation dose that reaches the icy shell, helping to preserve the stability and habitability of the secret ocean hidden below. It is a silent, invisible barrier that has likely safeguarded this vast reservoir of liquid water for billions of years, making Ganymede not just a geological wonder, but a sanctuary, a moon that built its own fortress to protect the most precious resource in the universe. But if you think Jupiter's magnetic field is powerful, or that a solar flare is a fearsome release of energy, then prepare to have your entire conception of magnetic power completely rewritten. We now step beyond the realm of planets and stars and into the territory of the true magnetic monsters of the cosmos. These are magnetars, the remnants of stellar giants that have collapsed into the universe's most powerful and terrifying magnets. To even begin to grasp their strength, consider this. A typical magnetar possesses a magnetic field that is 1,000 trillion times more powerful than Earth's. If a magnetar were located halfway between the Earth and the Moon, its magnetic field would effortlessly erase the magnetic strip on every credit card on the planet. It is a level of force so extreme it actually warps the very nature of reality itself, bending and twisting the atomic structure of matter. These incomprehensible objects are born from violence on a scale we can scarcely imagine. They begin their lives as massive stars, many times heavier than our Sun. When such a star exhausts its nuclear fuel, its own immense gravity causes it to collapse in on itself in a cataclysmic supernova explosion. What remains is an ultra-dense core, a neutron star. But for a special subset of these neutron stars, the conditions are just right for an astronomical perfect storm. As the star's core collapses, its already powerful magnetic field is compressed and amplified to ludicrous levels, like a cosmic dynamo spinning faster and faster until it reaches a breaking point. This process, known as flux conservation, transforms an already extreme object into a magnetar, a celestial entity where magnetism is the dominant force governing its existence. The sheer power contained within a magnetar's magnetic field doesn't just sit idly by. It manifests in the most dramatic way possible through colossal cosmic tremors known as starquakes. The crust of a neutron star is not a smooth, solid surface, but an incredibly rigid, crystalline structure, likely made of iron nuclei packed into a lattice. The unimaginable strain of the magnetic field, which is constantly trying to rearrange itself, puts immense stress on this crust. Eventually, the crust can no longer contain the pressure it cracks. This is a starquake, but this is no planetary tremor. The energy released in this single event is apocalyptic. When the crust fractures, it unleashes a titanic burst of energy, primarily in the form of gamma rays, the most energetic form of light in the universe. In a mere tenth of a second, a single magnetar flare from a starquake can release more energy than our Sun will emit over its entire 10 billion-year lifespan. These gamma-ray flares can be detected from clear across the galaxy, briefly outshining every other gamma-ray source in the Milky Way combined. One such event, recorded in 2004, originated from a magnetar 50,000 light-years away, and yet its blast was so powerful that it actually compressed Earth's ionosphere and significantly disturbed radio communications worldwide. From halfway across the galaxy, this magnetic monster reached out and touched us, a stark reminder of the ferocious forces at play in the universe. A magnetar is the ultimate expression of magnetic power, a testament to the fact that in the right extreme conditions, this fundamental force can become the most destructive and awe-inspiring phenomenon in the cosmos. Now, if a magnetar represents the ultimate, terrifying power of a magnetic field, then its slightly more stable cousin offers one of its most elegant and useful applications. We've arrived at the pulsar, a celestial object that has transformed our understanding of the cosmos not through raw destructive power, but through its breathtaking, clockwork precision. These are the cosmic lighthouses, and their story begins with the same violent birth as a magnetar, the supernova death of a massive star. What remains is a rapidly spinning neutron star, a city-sized ball of ultra-dense matter so compact that a single teaspoon of it would weigh billions of tons on Earth. But for this neutron star to become a pulsar, it needs one more crucial ingredient: a devastatingly strong and dramatically misaligned magnetic field. This is where the magic happens. The magnetic field of a typical pulsar isn't just strong. Its axis is tilted relative to the star's axis of rotation. Think of it like a colossal bar magnet stuck through the star, but pointing off in a completely different direction from its north and south poles. At the magnetic poles of this spinning neutron star, the field lines are funneled into incredibly narrow, focused beams. Charged particles, accelerated to near light speed by the intense magnetic forces, are forced to spiral along these field lines. This process generates powerful beams of radiation that shoot out from the magnetic poles, not unlike the focused beam of a lighthouse. But this is no ordinary light. It can blast out across the entire electromagnetic spectrum. From radio waves we can detect with giant dishes on Earth to high-energy gamma rays. The iconic pulse that gives these objects their name comes from a simple geometric effect. As the neutron star rotates at mind-bending speeds, often hundreds of times per second, these beams of radiation sweep through space like the beacon of a cosmic lighthouse. From our fixed vantage point on Earth, we only see a flash of light each time one of those beams swings across our line of sight. The star itself is emitting radiation continuously, but we perceive it as a rapid, rhythmic pulse. The timing of these pulses is what makes pulsars so extraordinary. The rotation of a neutron star is one of the most stable periodic processes in the entire universe. Once its spin is established, it can continue with a consistency that rivals our most advanced atomic clocks, losing or gaining only a fraction of a second over millions of years. This incredible reliability has made pulsars indispensable tools for astronomy. They are, in effect, nature's own GPS system for the galaxy. By carefully timing the pulses from an array of these cosmic clocks scattered across the Milky Way, astronomers can create a precision navigation grid, allowing them to triangulate positions and measure distances across the vast interstellar void with unprecedented accuracy. The discovery of the first binary pulsar system provided the first indirect evidence for the existence of gravitational waves, a prediction of Einstein's theory of general relativity that would later earn its discoverers a Nobel Prize. By tracking the incredibly slight changes in the pulse timing as two neutron stars orbited each other, scientists could see they were losing energy in exactly the way predicted if they were emitting ripples in spacetime itself. So, from a terrifying stellar corpse, we get a gentle, rhythmic ticking, a magnetic metronome in the darkness that allows us to map the galaxy and test the fundamental laws of the universe itself. For billions of years, a vast, cold cloud of gas and dust drifts silently in the interstellar void, held in a state of perfect, frozen equilibrium. Its own gravity is constantly pulling it inward, trying to initiate a collapse that would birth a new star. But for ages, something has been holding that collapse at bay, providing a hidden support structure against the relentless pull of gravity. That something is an interstellar magnetic field, threading through the cloud like an invisible skeleton. This force is the great moderator of star birth, the cosmic midwife that doesn't initiate the process, but carefully controls its pace and ultimately makes it possible. This delicate balancing act is a fight between two fundamental forces. Gravity is the great unifier, always seeking to pull matter together, to compress and condense it. Opposing it is magnetic pressure. The gas within these molecular clouds is not neutral. It's ionized, meaning it's filled with charged particles. These particles become trapped, forced to spiral along the magnetic field lines that permeate the entire cloud. This effectively makes the field lines behave like stiff, elastic rods. As gravity tries to compress the cloud, it must also compress these magnetic field lines. The lines push back, creating a form of pressure that can support the cloud against its own weight for millions of years, dramatically slowing the process of stellar gestation. It's only when the cloud grows massive enough that its gravity can finally overwhelm this magnetic support, or when a shockwave from a nearby supernova violently compresses the cloud and the field lines within it, that the great collapse can truly begin in earnest. Once the collapse starts, a new and even more fascinating magnetic problem emerges, the problem of spin. As any large cloud of gas begins to contract, even the tiniest amount of inherent rotation becomes amplified, a consequence of the conservation of angular momentum, the same principle that causes an ice skater to spin faster as they pull their arms in. If this process went unchecked, the spinning cloud would flatten into a disk long before a star could form at the center, and the centrifugal force would become so powerful that no more material could fall inward. The protostar at the center would be starved of fuel, unable to grow to the mass required to ignite nuclear fusion. It seems like a fundamental roadblock to creating a star. This is where magnetic fields perform one of their most elegant tricks: magnetic braking. Imagine the forming star and its disk spinning rapidly, with magnetic field lines rooted in the central protostar and extending far out into the slower-moving outer regions of the cloud and the surrounding interstellar medium. These field lines act like anchor lines thrown into a calm sea from a speeding boat. The rapidly rotating central region tries to drag these field lines around with it, but the distant, anchored parts of the field resist this motion. This creates a powerful drag force that acts as a brake, efficiently siphoning angular momentum away from the inner system and transferring it to the outer cloud material. This process allows the inner disk to slow down, enabling vast amounts of gas to lose its spin and fall down onto the growing protostar, feeding it the mass it needs to finally become a star. Without this magnetic braking system, star formation would be a messy, inefficient, and perhaps even failed process. Stars would be smaller, rarer, and might not form at all in the way we understand. The magnetic field, by first supporting the cloud and then by carefully managing its spin, acts as the essential regulator. It ensures the collapse is controlled and that the precious building blocks of a solar system can coalesce efficiently, setting the stage not just for the birth of a star, but for the eventual formation of planets that might one day orbit it. As the magnetic fields guide the birth of a star, their work is far from over. They now face their next great challenge: orchestrating the construction of planets from the chaotic debris left behind. This takes place in the protoplanetary disk, a vast, swirling, pancake-shaped cloud of gas and dust that encircles the newborn star. For decades, a fundamental puzzle plagued astronomers. This disk should be a remarkably smooth and placid place. The particles within it orbit the star in neat, quiet Keplerian bands, with material closer in moving faster than the material farther out. In such a calm, orderly environment, the tiny specks of dust and ice should simply continue their endless, gentle orbits. There's no obvious mechanism for them to bump into each other, stick together, and begin the long journey of building planets. The solution to this cosmic conundrum, it turns out, was hidden in the magnetic nature of the disk itself, through a process of brilliant instability. The key is that the protoplanetary disk is not a neutral gas. It's a weakly ionized plasma. Cosmic rays and radiation from the young star strip electrons from some of the gas atoms, creating a soup of charged particles. And where you have moving charged particles and magnetic fields, fascinating physics can occur. The star's magnetic field threads through the entire disk, and this sets the stage for a phenomenon called magnetorotational instability, or MRI. This is the hidden engine that stirs the pot and transforms a quiet disk into a turbulent cosmic construction zone. Imagine two parcels of gas orbiting the star on the same magnetic field line, like two beads on a stiff, invisible wire. The inner bead, being closer to the star, orbits faster than the outer bead. Now, because they are connected by this magnetic field line, the faster-moving inner bead acts like it's trying to drag the outer bead along, speeding it up. According to the laws of orbital motion, if you speed up a parcel of gas, it wants to move to a higher, slower orbit. Conversely, the outer bead, moving slower, acts as an anchor, trying to hold back the inner bead. Slowing down the inner parcel causes it to fall to a lower, faster orbit. This creates a runaway effect. The inner material falls inward while the outer material is pushed outward. This constant tug-of-war generates incredible friction and shearing forces, churning the entire disk into a state of vigorous turbulence. It's this magnetic instability that provides the vital stirring motion, ensuring that dust grains have countless opportunities to collide and coalesce. This magnetic turbulence serves two absolutely critical functions in planet formation. First, it is the primary mechanism for angular momentum transport. Remember the problem of spin that magnetic braking solved for the star itself. A similar issue exists for the disk. For material to fall inward and feed the growing star, it must lose its orbital angular momentum. The turbulent motions generated by the MRI provide an efficient way to transfer that spin outward through the disk, allowing gas to gradually spiral inward onto the star. Without this process, the young star might not be able to gather enough mass to truly ignite. Second, and perhaps more importantly for building planets, this turbulence is the catalyst for dust aggregation. In a perfectly smooth disk, microscopic dust grains would simply drift toward the star at their own leisurely pace, never meeting another grain. But in the churning, chaotic environment stirred up by the MRI, these grains are constantly jostled, colliding at low speeds. When they bump into each other, electrostatic forces, the same ones that make dust cling to your TV screen, can make them stick together. Over time, these microscopic collisions build up larger and larger aggregates, from fluffy dust bunnies to pebbles, to rocks, and eventually to massive mountain-sized bodies called planetesimals, the true building blocks of planets. The magnetic field, through the invisible hand of the magnetorotational instability, doesn't just create the chaos. It masterfully directs it, turning a quiet disk of potential into a dynamic nursery where worlds are patiently, collision by collision, assembled. Yet for all their destructive potential, these galactic cosmic rays do not travel across the universe in clean, straight lines. Their journey to Earth is anything but direct. Instead, they are forced to navigate a complex and chaotic obstacle course, a labyrinth of magnetic fields that fills the entire Milky Way galaxy. This interstellar medium is not empty. It is threaded through with a web of magnetic force lines, a relic field that is tangled, twisted, and turbulent, woven into the fabric of space itself by countless supernova and stellar winds over billions of years. When a high-energy proton or atomic nucleus enters this maze, its path is immediately and utterly scrambled. Because these cosmic rays are electrically charged particles, they cannot ignore magnetic fields. The instant they encounter one, the fundamental Lorentz force takes over, compelling them to spiral tightly around the magnetic field lines. They are no longer traveling in a straight line from their source. They are locked into a helical path, corkscrewing along the direction of the magnetic field. But the galaxy's magnetic field is not a neat, organized grid. It is a turbulent sea of fluctuations, with field strengths and directions changing dramatically over relatively short distances. As a particle zips from one magnetic domain to another, its trajectory is constantly being bent, refocused and redirected in a random walk across the cosmos. It's like trying to walk a straight line through an endless hall of mirrors where the walls are constantly shifting. You may eventually get somewhere, but your path will be a tangled mess that bears little resemblance to a direct route. This relentless magnetic scattering has a profound consequence for astronomy. It completely obscures the origins of these particles. By the time a cosmic ray finally, and randomly, intersects with Earth's atmosphere, it has been bounced around so many times that its incoming direction on the sky tells us absolutely nothing about where it began its journey millions of years ago. The particle arriving from what looks like the constellation Orion may have actually originated in a supernova remnant on the completely opposite side of the galaxy. This is the astronomer's frustration. We are constantly bombarded by these incredible messengers from the most violent events in the universe. but they arrive at our doorstep with their return addresses thoroughly erased by the magnetic maze of the galaxy. It forces us to be clever, to build enormous detectors to measure their energy and composition, piecing together clues about their sources indirectly, forever working to unravel the magnetic mystery that hides the cosmos's most powerful particle accelerators from our view. But if the journey of a single cosmic ray is a random walk through a magnetic maze, the maze itself is a structure of breathtaking scale and complexity. This brings us to the grand architecture of our own galaxy, the Milky Way's magnetic field. We often picture our home galaxy as a majestic pinwheel of stars, but that visible disk is cradled within an invisible skeleton, a vast web of magnetic force lines that stretches for tens of thousands of light years. This isn't a single, simple bar magnet. It's a turbulent, messy, and dynamic field that wraps around the galaxy's spiral arms, threads through its colossal gas clouds, and shapes the very ecosystem between the stars. How can we possibly map something so vast and completely invisible? Astronomers have developed some brilliantly clever techniques. One primary method involves studying starlight itself, but not just its brightness or color. As light travels through the galaxy, it can become polarized. This means its light waves, which normally vibrate in all directions, become preferentially aligned in one plane. This happens when the light passes through clouds of interstellar dust that are themselves aligned by a magnetic field. The dust grains are not spherical. They are more like tiny, cosmic needles. A galactic magnetic field causes these microscopic needles to line up, like compasses all pointing in the same direction. When starlight passes through this filtered cloud, it becomes polarized. By carefully measuring the angle of polarization for the light from thousands of distant stars, astronomers can essentially trace the orientation of the magnetic field lines across vast distances, building a map of the field's direction throughout the disk of the galaxy. Another powerful tool comes from listening to the radio sky and observing a specific type of emission called synchrotron radiation. This is the light given off by high-energy electrons as they are forced to spiral at nearly the speed of light around galactic magnetic field lines. It's the same basic process that creates the light in a particle accelerator on Earth, but on a galactic scale. This synchrotron radiation is also highly polarized, and its intensity directly reveals the strength of the magnetic field that's doing the accelerating. By combining these two methods, polarized starlight and polarized synchrotron radio waves, scientists can painstakingly piece together a three-dimensional picture of this magnetic skeleton, inferring its strength, its direction, and how it intertwines with the galaxy's spiral structure. This invisible framework is far from a passive decoration. It is a fundamental actor in the galactic drama. It structures the interstellar medium, the thin soup of gas and dust between the stars. The magnetic field provides a supporting pressure that helps hold giant molecular clouds together against their own turbulence, much like the invisible steel beams in a skyscraper. It also influences the flow of gas on epic scales, guiding the collapse of clouds to form new stars and shaping the expanding shells of debris from dying stars. Perhaps its most crucial role, as we've seen, is as a galactic prison for cosmic rays. The field acts as a magnetic confinement system, trapping these high-energy particles within the galaxy for millions of years, bouncing them back and forth across the vast gulf between spiral arms. Without this magnetic cage, these particles would simply fly off into intergalactic space, and the intense radiation environment that helps drive chemistry in interstellar space would be vastly different. The Milky Way's magnetic field is the silent architect of our galactic environment, an unseen force that organizes the chaos, contains the most energetic particles, and quietly guides the eternal cycle of stellar birth and death. But the journey of a single charged particle doesn't end with simply being trapped. It has one final, spectacular way to announce its presence and reveal the very fields that confine it. When an electron is caught in the grip of a powerful magnetic field and accelerated to a significant fraction of the speed of light, it is forced to emit a very special kind of light. This is not the gentle glow of a heated filament or the specific color given off by an excited atom. This is synchrotron radiation, a brilliant, broad-spectrum beacon that is the direct and unmistakable signature of relativistic electrons dancing on magnetic field lines. The physics behind this phenomenon is both elegant and extreme. Imagine a single electron moving at 99% the speed of light. A magnetic field exerts a force on a moving charged particle that is always perpendicular to its direction of motion. This force doesn't slow the electron down, but it constantly changes its direction, forcing it onto a tight, helical path, corkscrewing along the magnetic field. According to the laws of electromagnetism, any charged particle that is accelerated will emit radiation. In this case, the electron is undergoing a tremendous continuous acceleration as it is whipped around in a circle. But for particles moving this fast, the radiation isn't emitted in all directions like a light bulb. Due to the mind-bending effects of Einstein's special relativity, the emission is concentrated into an incredibly narrow, searchlight-like beam that shoots out directly ahead of the particle in its direction of motion. To an observer, this looks like a brilliant, fleeting flash of light every time the electron's beam sweeps across their line of sight, creating an intensely focused and powerful signal. This synchrotron light has a very distinctive character. It is polarized, meaning its light waves are aligned in a specific direction that relates to the orientation of the magnetic field. Even more importantly, its spectrum is completely different from thermal radiation. Instead of peaking at a specific color like the light from a star, synchrotron radiation is a continuous smear of energy across the entire electromagnetic spectrum, from low-frequency radio waves all the way up to high-energy X-rays and gamma rays. The exact shape of this spectrum tells astronomers precisely how energetic the electrons are, and how strong the magnetic field is that's whipping them around. It is a direct readout of the physical conditions in some of the most violent environments in the universe. This makes synchrotron radiation one of the most powerful diagnostic tools in all of astronomy. It acts as a natural highlighter, painting the invisible magnetic fields of the cosmos in brilliant light. When we look at the intricate filaments of a supernova remnant like the Crab Nebula, we are not seeing glowing gas in the traditional sense. We are seeing synchrotron radiation, tracing out the incredibly powerful magnetic fields that are accelerating electrons to relativistic speeds within the expanding shock wave. The vast, radio-emitting lobes that extend for millions of light-years from active galaxies are not hot gas. They are colossal reservoirs of magnetic energy and fast-moving electrons, their synchrotron glow revealing the structure and power of jets blasted out by supermassive black holes. Even the faint radio haze emanating from massive galaxy clusters is synchrotron radiation, betraying the presence of diffuse magnetic fields and particle acceleration on the very largest scales. In every case, this unique light allows us to see the unseen, transforming the invisible architecture of magnetic force into a visible, measurable map of the universe's most dynamic and energetic places. At the very heart of a massive galaxy, a true monster lies in wait, a supermassive black hole with the mass of millions or even billions of suns, all crushed into a single point of infinite density. But its most terrifying feature isn't its gravity well, from which not even light can escape. It's what happens just outside that point of no return, where this cosmic beast transforms into the most powerful particle accelerator in the universe, firing colossal jets of matter across hundreds of thousands of light years. These are not gentle streams. They are tightly focused beams of plasma, moving at over 99% the speed of light, punching clear through the galaxy and far out into intergalactic space. For scale, if such a jet were aimed at our solar system from a nearby galaxy, its effects would be catastrophic. but its very existence is a testament to the unbelievable power of magnetism harnessed by a black hole. The raw energy for these jets doesn't come from the black hole itself, but from the chaos surrounding it. As a black hole feasts on stars, gas, and dust, this material doesn't fall straight in. Instead, it forms a swirling, superheated whirlpool of plasma called an accretion disk, orbiting at a significant fraction of light speed. The friction within this disk heats it to millions of degrees, causing it to glow brilliantly across the entire electromagnetic spectrum. This is an active galactic nucleus, or AN, one of the most luminous objects in the cosmos. Yet for all the light it produces, it can channel orders of magnitude more energy into these invisible jets, and that process requires a conductor, a set of physical laws that can extract the rotational energy of the black hole itself and focus it into a narrow, deadly beam. This is where magnetic fields perform their most spectacular act of engineering. The accepted theory, known as the Blandford-Zienagic process, describes a mechanism so elegant it seems almost like science fiction. Imagine the intensely magnetized plasma of the accretion disk. As the black hole spins, it literally drags the fabric of space-time around with it, an effect known as frame dragging. The magnetic field lines, which are frozen into the ionized gas of the disk, get caught up in this spiraling motion and are wound up like an enormous cosmic spring. These field lines become twisted into an incredibly tight coil, storing a titanic amount of energy and creating a powerful magnetic pressure that has to go somewhere. The rotating black hole, acting like a gigantic dynamo, now induces enormous voltages along these twisted field lines. This creates a powerful electric field that rips charged particles, electrons and their antimatter counterparts, positrons, out of the accretion disk plasma and accelerates them to relativistic speeds. But acceleration alone isn't enough to create the jets we see. They need to be focused. This is the magnetic field's second masterstroke. The tightly wound bundle of magnetic field lines acts like the nozzle of a gigantic garden hose, constricting the flow of these high-energy particles into two incredibly narrow, oppositely directed beams that fire out along the black hole's rotational axis, the only path of least resistance. This magnetic nozzle is so effective at collimating the beam that it can remain pencil-thin for distances that dwarf entire galaxies, a feat of focusing that defies belief. We can see the awesome after-effects of this magnetic cannon fire throughout the universe. When these relativistic jets slam into the tenuous gas that exists between galaxies, they don't just stop. They create massive, balloon-like structures known as radio lobes. These lobes glow brightly with synchrotron radiation, the telltale sign of electrons spiraling at near light speed around magnetic field lines. In some cases, these jets can even be disrupted by their own interaction with the intergalactic medium, puffing up into immense, wispy structures that resemble the smoke rings from a celestial explosion. These jets are the black hole's feedback mechanism, a way of releasing so much energy into its surroundings that it can shut down star formation in an entire galaxy, heat the gas for a whole galaxy cluster, and ultimately dictate the growth and evolution of the largest structures in the cosmos. They are the ultimate expression of magnetic power, a force that can tap into the spin of a singularity and use it to write its signature across the universe for all to see. However, the conventional picture of a perfectly spherical explosion is being challenged, and a compelling new ingredient is emerging as a potential game-changer in this stellar drama: intense magnetic fields. The core collapse process itself creates the perfect conditions for a magnetic powerhouse. As the iron core implodes, it doesn't just get denser, it also spins faster, a consequence of conserving angular momentum, much like an ice skater pulling their arms into spin. This newborn, rapidly rotating proto-neutron star acts as a colossal dynamo, and the infalling material from the outer layers of the star gets wound around it like a cocoon. This differential rotation can stretch and amplify any pre-existing magnetic field from the progenitor star to truly monstrous strengths, transforming it in mere seconds from a modest stellar field into a magnetar-level force. This newly forged magnetic field may be the crucial catalyst that breaks the spherical symmetry and finally revives the stalled shockwave. Think of the proto-neutron star as a powerful engine, humming with rotational energy and neutrino heat, but that energy is trapped at the center. The magnetic field, now wound up into an incredibly tight coil, acts as a conduit, a way to transport that energy outward. The field lines, frozen into the seething plasma, can get so twisted that they buckle and erupt, violently transferring vast amounts of energy and momentum from the rapidly spinning core up into the stalled shock. This isn't a gentle push. It's more like a magnetic piston driving into the shock front, reinvigorating it from within and helping to blow the overlying stellar material away. The result is not a clean, spherical boom, but a violently lopsided explosion. This magnetic mechanism provides an elegant explanation for one of the most persistent mysteries in supernova observations: why the remaining neutron star often gets a powerful kick, flying away from the explosion site at hundreds of miles per second. If the explosion is channeled and focused by these intense magnetic fields, ejecting more material in one direction than another, the conservation of momentum will literally rocket the newborn neutron star in the opposite direction. We see this in the wild, off-center trajectories of many pulsars, zipping through the galaxy on paths that are almost impossible to explain with a perfectly symmetrical model. Furthermore, these fields are likely responsible for launching some of the most narrow and energetic jets of material ever seen, which could be the origin of certain types of gamma-ray bursts linked to supernova. So, what we witness as a brilliant, seemingly chaotic stellar death may, in fact, be a carefully directed and channeled explosion, sculpted and powered at the most critical moment by the invisible hand of magnetism. But to truly map the vast and invisible magnetic architecture of the cosmos, astronomers needed a tool that could measure these fields from mind-boggling distances, a way to turn light itself into a cosmic magnetic probe. This brings us to a subtle yet profoundly powerful phenomenon known as Faraday rotation, a fundamental interaction between light and magnetism that allows us to take the measure of the universe's hidden forces. It all begins with the nature of light itself. While we often think of it as a simple wave, it also has a property called polarization, which describes the specific orientation in which its electric field vibrates. Think of it like this: if light were a wave traveling along a rope, a polarized wave would be one where the rope is only being shaken up and down, not side to side. This polarized light is common in the universe, often created when starlight scatters off dust grains or is emitted by synchrotron radiation. Now, imagine a beam of this polarized light traveling through the void. If it passes through a region of space that contains both free-floating electrons and a magnetic field, something remarkable happens. The magnetic field causes the electrons to wiggle or oscillate in a very specific way. As the light wave passes by, it interacts with these wiggling electrons. This interaction causes the plane of the light's polarization to slowly rotate, like a compass needle turning, as it journeys through the magnetized medium. The stronger the magnetic field and the more electrons there are along the path, the greater the amount of rotation. It's a tiny effect for any single electron, but over the immense distances between stars and galaxies, these minuscule twists add up to a measurable change that we can detect with our telescopes. This is Faraday rotation, a subtle twist imprinted on starlight that carries a direct message about the magnetic environment it traveled through. For astronomers, this effect is nothing short of a revolution in remote sensing. They use incredibly bright and distant sources of polarized radio waves, often quasars or pulsars, as their cosmic flashlights. By the time this polarized light reaches our telescopes on Earth, its polarization angle has been rotated from its original orientation. The key is to measure this rotation at multiple different frequencies. The amount of rotation depends on the wavelength of the light. Longer wavelengths are rotated more than shorter ones. By carefully measuring how much the polarization angle changes across a range of frequencies, scientists can calculate a single, crucial number known as the rotation measure. This number is the Rosetta Stone. It combines the strength of the magnetic field along the line of sight with the density of electrons it passed through. By cleverly combining rotation measure data with other methods that estimate the electron density, astronomers can isolate and solve for the magnetic field strength, effectively using light to weigh an invisible force field across light years of space. This technique has opened a window into magnetic structures we could never hope to see directly. It allows us to probe the tangled magnetic fields woven through the spiral arms of our own galaxy, measuring their strength and even determining their direction, whether they are pointing toward us or away from us. We can study the magnetized lobes of giant radio galaxies, map the fields in the vast clusters of galaxies, and even detect the faint magnetic imprint in the seemingly empty voids between them. Every time a distant quasar's light twinkles with the telltale sign of Faraday rotation, it is drawing a map for us, a line of magnetic force written in the language of twisted light, revealing the hidden skeletal structure that supports and shapes the universe on the very largest scales. And in the heart of these cosmic explosions, from our sun's tantrums to the fury of distant black holes, lies a single, universal trigger, a sudden and explosive reconfiguration of magnetic fields known as magnetic reconnection. This isn't a gentle bending or a slow drift. It's a fundamental breaking of the rules, a process where magnetic field lines, which normally repel each other like opposing sides of a magnet, are forced together under immense pressure until they snap. In that violent instant, they shatter their old connections and form new, lower energy ones, unleashing a catastrophic flood of pent-up energy that was stored in the twisted field. It is the universe's primary mechanism for converting the invisible energy of magnetism into the palpable fury of heat and motion, a switch that gets flipped in plasma throughout the cosmos to power its most spectacular displays. The simplest way to picture this is with a simple thought experiment. Imagine two powerful bar magnets, their north poles held dangerously close to each other. They naturally repel, pushing against one another, and it takes energy to hold them in that tense, unstable position. Now imagine those magnets are not solid, but are instead made of elastic bands, lines of magnetic force frozen into a superheated plasma. As more and more pressure is applied, these elastic bands get stretched tighter and tighter, storing colossal amounts of energy in their tension. This is the state of the sun's corona, where the churning motion of the plasma below constantly winds up the magnetic field into complex, stressed knots. The system is desperate to find a more stable, relaxed state, but it's stuck. It needs a catalyst, a way to break the deadlock. That catalyst is magnetic reconnection. When the stress becomes too great, or when a wave of turbulence forces the field lines just a little too close together, something extraordinary happens. At a specific, critical point, the plasma can no longer sustain the opposing magnetic pressures. The insulating properties of the plasma break down, and the field lines are no longer frozen in. They effectively break, and in a flash, they reconnect in a new, entirely different configuration. It's like cutting two taut, crossed rubber bands and then swiftly tying the opposite ends together. The new arrangement is far more relaxed, but all the energy that was stored in the stretched bands has to go somewhere. In that single, explosive moment, it is converted into two powerful forms: intense heat that sends temperatures soaring into the millions of degrees, and kinetic energy that violently flings the newly freed plasma away from the reconnection site at tremendous speeds. This creates two powerful jets of material shooting out in opposite directions, a signature of the reconnection process. We see the effects of this process everywhere we look in space. It is the fundamental trigger for solar flares and coronal mass ejections. The vast, looped structures you see in images of the Sun are arcs of magnetic field holding plasma aloft. When reconnection occurs, it's like cutting the wires holding a suspended weight. The stored magnetic energy is released, accelerating particles to near light speed and heating the local atmosphere to incredible temperatures in a flash of X-rays and ultraviolet light. Closer to home, this same process is a major driver of space weather that affects Earth. When the solar wind, with its own embedded magnetic field, collides with Earth's magnetosphere, their field lines can become pressed together. When they reconnect on the sun-facing side of our planet, they open portals that allow solar wind particles to funnel directly into our magnetosphere, feeding the auroras and energizing our radiation belts. It's this constant magnetic negotiation between the Sun and Earth that shapes the very space environment our satellites and astronauts must navigate. But the influence of magnetic reconnection extends far beyond our solar neighborhood. It is now believed to be a key engine in powering the relativistic jets from supermassive black holes and in accelerating particles in supernova remnants. In these extreme environments, the magnetic fields are unimaginably strong, and the amounts of energy they can store and then suddenly release through reconnection are truly apocalyptic, capable of lighting up the gamma-ray sky across billions of light years. This fundamental process, once an obscure concept in plasma physics, is now recognized as a universal key, the primary mechanism the cosmos uses to unlock the vast reservoirs of energy stored in its invisible magnetic skeletons, transforming them into the brilliant and violent fireworks that illuminate the darkness. Drifting between the stars, far from the brilliant heat of any sun, lies the raw material of future worlds. This is the interstellar medium, a frigid and seemingly empty void. But this cosmic emptiness is an illusion. It is in fact a diffuse ocean of gas and dust, and it is held together by an invisible scaffolding of magnetic force. These fields provide a crucial form of pressure support, acting against the relentless pull of gravity and the turbulent motions within the clouds themselves. Without this magnetic skeleton, these vast nebulae would either dissipate into nothingness or collapse into stars far too quickly, drastically altering the rhythm of galactic evolution. It is this delicate balance between magnetic pressure and gravitational contraction that sets the pace for star birth, making these fields the great moderators of galactic life cycles. This magnetic influence is visibly written into the very shapes of these cosmic clouds. Look at images of iconic nebulae, and you'll see they are rarely simple, blobby spheres. They are stretched into long, filamentary tendrils and intricate, wispy structures. These forms are a direct result of the interstellar magnetic field threading through the cloud. The ionized particles within the gas become trapped, forced to spiral along these field lines. This effectively makes the magnetic field lines behave like stiff, elastic rods embedded within the cloud, resisting any motion that would compress them across their length. Gravity and turbulence can more easily pull material along the direction of the field lines, leading to the formation of these elongated, ribbon-like structures rather than perfect spheres. The magnetic field imprints its own architecture onto the gas, sculpting the nurseries where stars will eventually be born. Perhaps the most crucial role of this magnetic scaffolding is as a regulator, a braking system on the process of gravitational collapse. A molecular cloud might have enough mass for gravity to eventually win, but the magnetic field ensures it's not a runaway process. The field provides a powerful supporting pressure that can hold the cloud in a state of equilibrium for millions of years. It's only when the cloud grows massive enough that its gravity can finally overwhelm this magnetic support, or when an external shockwave from a nearby supernova violently compresses the cloud and the field lines within it, that the collapse can begin in earnest. This magnetic resistance is why the universe isn't constantly ablaze with the furious birth of stars. It introduces a necessary delay, a period of gestation that allows the cloud to fragment and structure itself properly, ultimately leading to the formation of not just stars, but entire planetary systems. Finally, these hidden fields leave a detectable signature for astronomers, a way for us to map the invisible. The dust grains within these clouds are not spherical. They are more like tiny, cosmic needles or flat platelets. A pervasive magnetic field causes these microscopic grains to align themselves, much like countless compass needles all pointing in the same direction. When starlight from a distant star behind the cloud travels through this filtered, dusty medium, something subtle happens. The dust grains preferentially absorb starlight that is vibrating in one particular plane. This process, called interstellar polarization, means the light that emerges from the other side of the cloud is no longer vibrating in all directions. It is polarized, its waves now aligned with the orientation of the magnetic field that aligned the dust. By measuring the angle of this polarization for the light of thousands of stars, astronomers can trace the direction of the magnetic field lines across the entire galaxy, painting a map of the invisible scaffolding that holds the cosmos together. We have traced the immense power of magnetic fields from the hearts of stars to the voids between galaxies. But this journey leaves us with one of the most profound questions in all of cosmology. Where did they come from in the first place? How does a universe born from a hot, featureless soup of energy and particles, a state where such structures could not exist, somehow weave these invisible lines of force into the very fabric of spacetime itself? This is the mystery of cosmic magnetogenesis, the quest to find the origin of the very first magnetic fields. And the answer lies in the extreme physics of the universe's first moments. The primordial universe immediately after the Big Bang was a place of incredible symmetry and smoothness. The searing heat and density would have likely erased any primordial magnetic fields that might have existed, and the simplest models suggest the universe was born magnetically neutral. For a magnetic field to exist, you need moving electric charges to create electric currents. And in those first moments, the universe was too symmetric, too uniform for such structures to form. So, the fields we see today, threading through every galaxy and nebula, must have been seeded by some later process, a tiny, fragile imprint that would then need to be nurtured and amplified to galactic scales over billions of years. Scientists have several compelling hypotheses for how these initial, seed fields might have been generated. One of the leading ideas involves a phenomenon that occurred when the universe was just a fraction of a second old, during a period known as inflation. This was a moment of hyper-accelerated expansion, where quantum fluctuations, tiny, random jitters in the energy fields that filled the cosmos, were stretched to macroscopic sizes. It's possible that during this violent expansion, some of these quantum fluctuations could have generated minuscule electromagnetic waves, creating weak, large-scale seed fields that were then imprinted across the entire observable universe. Another possibility points to the aftermath of the Big Bang itself. As the newborn universe cooled and underwent phase transitions, much like steam condensing into water, these shifts in the fundamental state of matter could have created cosmic defects, cracks in spacetime that released energy in the form of primordial magnetic fields. These initial seeds, however, would have been almost unimaginably weak, billions of times fainter than the magnetic field holding a refrigerator magnet to your door. For them to grow into the powerful forces that shape galaxies, a universe-sized amplification system was required. This is where the dynamo effect, which we've seen at work in planets and stars, enters the story on a truly epic scale. The first stars and galaxies to form were turbulent and rapidly rotating. As their ionized gas collapsed and spun, it would have acted as a natural dynamo, stretching, twisting, and amplifying these weak seed fields. A small seed field, when wound up by the motion of a conducting fluid, can induce electrical currents that, in turn, generate a stronger magnetic field. This process, repeated over and over in the first generations of stars, provided the initial crucial boost, taking the quantum whisper of a field and turning it into something substantial. But the real cosmic workhorse for magnetic field amplification was the structure of the galaxies themselves. As protogalaxies merged and grew, their chaotic motions and powerful shock waves from supernovae would have further stirred this magnetized plasma. The magnetorotational instability in accretion disks around the first black holes would have generated tremendous turbulence, winding the fields ever tighter. Over billions of years, through countless cycles of star formation, supernova explosions, and galactic collisions, this dynamo action systematically converted the turbulent kinetic energy of the cosmos into magnetic energy. The weak, primordial seeds were continuously stretched, folded, and reinforced, their strength growing exponentially until they became the organized, pervasive fields we detect today. The majestic magnetic skeletons of modern galaxies are not primordial relics. They are a testament to a long and violent history of cosmic growth, built upon the faintest of beginnings. We have seen how magnetic fields weave through individual galaxies, but to find the very largest magnetic structures in the entire universe, we must pull our view back even farther, to the colossal gatherings of thousands of galaxies known as galaxy clusters. These are the true titans of the cosmos, the largest objects in existence held together by their own gravity. Within them, galaxies swarm like bees, but they are vastly outnumbered by an unseen ocean of superheated gas that fills the space between them. This intracluster medium is so hot it glows in X-rays, a thin plasma that has been heated to tens of millions of degrees. And it is within this seemingly chaotic and fiery void that astronomers have made a stunning discovery: a pervasive, invisible magnetic field that stretches across millions of light years, enveloping every galaxy in the cluster in a cosmic web of force. The sheer scale of these fields is almost impossible to comprehend. We are no longer talking about the magnetic field of a star or even a single galaxy. This is a field that defines the architecture of an entire cluster, a structure that could take light over 10 million years to cross. The field itself is incredibly diffuse and weak by cosmic standards, perhaps 1,000,000 times weaker than Earth's magnetic field, but its enormous volume means the total energy it contains is staggering. For a long time, these fields were completely invisible to us, their presence only revealed indirectly through their powerful effects on the space around them. So how did such vast magnetic skeletons form? The leading theory points to a process of incredible amplification over billions of years. It is believed that weak seed fields, perhaps originating from the earliest galaxies or active black holes, were present in the gas that eventually collapsed to form the cluster. As thousands of galaxies swarmed and merged in a chaotic gravitational dance, their motion churned the intracluster plasma into a state of extreme turbulence. This is where the dynamo effect works on its grandest possible scale. The turbulent motion of the conductive plasma would have stretched, twisted, and folded these weak magnetic field lines over and over, systematically converting the kinetic energy of the swirling gas into magnetic energy. It's a process of cosmic feedback, where the motion of the galaxies themselves amplifies the magnetic field, which then influences how the gas and even the galaxies themselves can move. A self-reinforcing cycle that has built these immense structures over the age of the universe. We cannot see these fields directly, but we can see their brilliant signature through the light they produce: synchrotron radiation. This is the key that unlocked the mystery. When astronomers pointed their radio telescopes at galaxy clusters, they didn't just see the quiet glow of individual galaxies. They detected a faint, diffuse radio haze permeating the entire cluster, a soft light that had no obvious source. The spectrum of this radiation was the unmistakable fingerprint of synchrotron emission, meaning it was created by electrons spiraling at nearly the speed of light around magnetic field lines. This was the definitive proof. The very existence of this radio glow meant two things. First, that a massive magnetic field must be present to force the electrons onto their spiral paths, and second, that a powerful natural particle accelerator must be at work within the cluster, boosting electrons to these incredible energies. This reveals the other critical role of these colossal magnetic fields. They are essential for accelerating particles to relativistic speeds. The turbulent motions that amplified the fields also create powerful shock waves that ripple through the intracluster medium, much like sonic booms on a cosmic scale. These shocks can accelerate electrons to a significant fraction of the speed of light. Once these high-energy electrons are injected into the magnetized plasma, they become trapped by the field lines, forced to spiral around them, and in the process emitting the synchrotron radio waves we detect. In some clusters, we see even more dramatic structures. Gigantic radio relics, which are immense, curved arcs of synchrotron emission that mark the location of colossal shock waves generated by galaxy collisions. And there are radio halos, vast, cloud-like regions of emission that seem to be powered by the turbulence from the merger itself. These features are not just spectacular to look at. They are a direct map of the magnetic field and the violent processes shaping these largest of all cosmic structures, proving that even in the vast spaces between galaxies, the invisible hand of magnetism is still at work, orchestrating the flow of energy and matter on a truly breathtaking scale. While the sun's magnetic heartbeat dictates space weather and paints our skies with auroras, a far more contentious question lingers. Could these cosmic cycles also be subtly tuning the very climate of our planet? This idea that the sun's 11-year magnetic cycle might influence Earth's long-term climate patterns sits at a fascinating and hotly debated intersection of solar physics and atmospheric science, a field where compelling hypotheses must navigate a complex web of evidence and skepticism. The proposed mechanisms are ingenious. The most straightforward link is through total solar irradiance, or TSI, the sheer amount of energy the sun emits. This isn't a constant, it varies slightly in sync with the sunspot cycle. At solar maximum, when the sun's face is dotted with magnetic sunspots, the overall output actually increases, but by a tiny fraction, about 0.1%. While this seems minuscule over the span of an 11-year cycle, this small fluctuation does inject a measurable pulse of extra energy into Earth's climate system. The challenge for scientists has been determining whether this tiny nudge is enough to produce significant and lasting climatic effects, or if it's simply absorbed by the planet's vast and complex weather systems with little overall impact. A more complex and controversial theory involves a fascinating celestial chain reaction mediated by the sun's magnetic field. This is the galactic cosmic ray hypothesis. When the sun is at its magnetic peak, its strengthened heliosphere and enhanced solar wind do a better job of deflecting galactic cosmic rays, those high-energy particles from deep space, away from the inner solar system. This leads to a measurable dip in the number of cosmic rays reaching Earth's atmosphere during solar maximum. Here's where the climate connection is proposed. These cosmic rays are thought to play a role in seeding clouds. As they slam into the atmosphere, they can ionize molecules, which in turn can act as nucleation sites for water vapor to condense around, potentially leading to increased cloud formation. The logic follows that fewer cosmic rays during a strong solar cycle mean fewer clouds, particularly low-level clouds which reflect sunlight back into space. With less sunlight reflected, more energy is absorbed by the Earth, potentially leading to a warming effect. It's an elegant idea, suggesting the sun's magnetic shield indirectly influences how much of its own energy our planet retains by controlling the cosmic rays that help make our clouds. Despite the intuitive appeal of these mechanisms, the overwhelming scientific consensus is that while solar forcing is a real phenomenon, its influence on modern climate change is dwarfed by the impact of human activities. Meticulous reconstructions of solar activity over centuries, drawn from ice core and tree ring data, show that while there is a correlation between prolonged solar minima like the Maunder minimum in the 17th century and cooler periods such as the Little Ice Age, the Sun's total energy output has shown no net upward trend since the mid-20th century, the same period during which global temperatures have skyrocketed. The warming predicted by solar variability alone is simply too small to account for the rapid and unprecedented heating we are now observing. The fingerprints of human influence, particularly from greenhouse gas emissions, match the observed warming pattern far more precisely and powerfully. This isn't to say the sun is irrelevant. It is, after all, the fundamental driver of our entire climate system. Rather, it places the sun's role in a crucial context. Its magnetic cycles provide a natural background rhythm to Earth's climate, a soft, periodic whisper of variability. But the modern warming trend is a roaring crescendo, an anomaly so large and so fast that it clearly overwhelms this natural solar background signal. Understanding the sun's influence is vital for painting the complete picture of Earth's climate history, but it also sharply defines the boundaries of that influence, making it abundantly clear that the primary force shaping our climate's urgent present and future is not the silent, magnetic conductor 93 million miles away, but the collective actions right here on the surface world. Yet for all their cosmic might, magnetic fields are not just forces that shape grand celestial structures. They also provide the most intimate and ancient of guides, written into the very biology of life on our own planet. We now step from the vastness of interstellar space to the intricate world of animal navigation, to a sense so subtle and profound it seems like magic: magnetosphere. This is nature's built-in compass, an innate ability for creatures across the animal kingdom to detect and utilize Earth's magnetic field to perform feats of navigation that defy belief. Consider the Arctic tern, a bird that embarks on an epic migration from the Arctic to the Antarctic and back again every year, a round trip of over 40,000 miles. Or the humble loggerhead sea turtle, hatched on a sandy beach in Florida, which swims out into the vast, featureless expanse of the Atlantic Ocean, only to return to that very same coastline years later to lay its own eggs. For decades, how these animals achieved such precise, long-distance navigation was one of biology's greatest mysteries. They clearly weren't just following landmarks or memorizing star patterns. They possessed a sixth sense, an ability to tap into the invisible lines of magnetic force that wrap around our planet, using them like a global grid of latitude and longitude. Scientists have discovered that this incredible sense is surprisingly widespread. It's found in animals as diverse as birds, sea turtles, salmon, lobsters, bats, and even certain bacteria. This suggests magnetosphere is an ancient sensory system, one that likely evolved very early in life's history. The question is, how does it work? How does a living organism, a collection of cells and chemicals, perceive something as intangible as a magnetic field? The search for the biological compass has led researchers down two fascinating and very different paths, each with compelling evidence but no definitive answer. The first theory proposes a mechanism that is, in principle, beautifully simple and direct: a physical compass made of a magnetic mineral. This hypothesis centers on tiny crystals of an iron oxide called magnetite. This mineral is naturally magnetic, and in certain bacteria, we know exactly how it works. These so-called magnetotactic bacteria literally string together a chain of magnetite crystals inside their bodies. This internal bar magnet forces the entire bacterium to align itself with Earth's magnetic field, like a microscopic compass needle, helping it orient itself in the water column. The discovery of similar magnetite crystals in the brains and beaks of birds and the noses of fish strongly suggests that more complex animals might use a similar, albeit more sophisticated, system. The idea is that these magnetite clusters are attached to specialized nerve cells. When the animal moves and changes its orientation relative to the magnetic field, the tiny magnetite grain tugs on its cellular anchor, stretching the cell membrane and triggering a nerve signal to the brain. It would be a direct, physical sensation of magnetic pull, a tangible force acting on a tangible object inside the body. The second leading theory is far more enigmatic and sounds like something from the realm of quantum biology. This model suggests that the compass isn't based on a mineral, but on a delicate, light-sensitive chemical reaction that is subtly influenced by magnetism. Here's how it's thought to work. Inside the retina of a bird's eye, a protein called cryptochrome may be the key. When a photon of blue light strikes this protein, it can kick off a complex reaction that creates a pair of molecules with unpaired electrons, known as a radical pair. These electrons are quantum mechanically entangled, meaning their spins are linked. The crucial point is that the rate of this chemical reaction and the state of these spinning electrons can be influenced by the direction and strength of the surrounding magnetic field. It's proposed that this could create a visual effect, a subtle, overlapping pattern of light or dark that is projected across the bird's visual field, a kind of heads-up display showing the direction of magnetic north. The animal wouldn't feel the field, it would literally see it as a faint compass superimposed on its view of the world. This would explain why many animals seem to need light to orient themselves magnetically. The debate between these two models, the physical magnetite compass and the chemical quantum compass, is far from settled. In fact, many researchers believe that some animals might use both systems in concert, each serving a different purpose. The magnetite system might provide a simple, robust sense of polarity, which way is north. The more delicate light-based system might instead sense the inclination of the field lines, the angle at which they dive into the Earth, which changes with latitude and could act like a magnetic map, telling the animal not just which way to go, but approximately where it is. This incredible sensory ability, whether based on physics or quantum chemistry, reveals a profound truth. Life has not merely evolved on a planet with a magnetic field. It has evolved to actively partner with it, weaving this invisible force into the very fabric of its behavior and ensuring its survival across the globe for millions of years. Deep within our planet, far beneath the familiar ground we walk upon, lies a furious, hidden ocean that holds the key to our existence. This is Earth's outer core, a 2,300-kilometer deep sea of swirling, molten iron and nickel, churning with unimaginable power. It is here, in this scorching, pressurized darkness, that our planet's magnetic heart beats a self-sustaining engine known as the geodynamo. This isn't a simple bar magnet frozen in time. It is a dynamic, living system, a continuous conversion of thermal and gravitational energy into magnetic force, and it has been running non-stop for at least 3.5 billion years, protecting our atmosphere and enabling life itself. The fuel for this engine comes from two profound sources of energy deep within the Earth. The first is the primal heat left over from the planet's violent formation over 4.5 billion years ago, the residual energy from countless asteroid collisions that built our world. The second, and perhaps more crucial today, is the latent heat released as the inner core slowly grows. At the very center of the Earth, under immense pressure, the inner core is a solid ball of iron and nickel, roughly the size of Pluto. It is not a static sphere. It is gradually freezing, crystallizing from the liquid outer core as our planet slowly cools. This process of solidification does two critical things. It releases a tremendous amount of latent heat, which rises like a plume, and it leaves behind a residue of lighter elements like oxygen, silicon, and sulfur in the surrounding liquid. These lighter elements are less dense than the pure molten iron, causing them to buoyantly rise towards the core mantle boundary. This combination of thermal heat and compositional buoyancy sets the liquid metal in motion, driving a vast, planetary-scale convective cycle. But churning metal alone is not enough to create a magnetic field. A chaotic, turbulent fluid would only generate a disordered, messy field that would quickly cancel itself out. To organize this motion into a coherent global dynamo, our planet calls upon a powerful force born from its own spin, the Coriolis effect. As the heated, buoyant fluid rises from the inner core and the cooler, denser fluid sinks from above, the rapid rotation of the Earth, one full turn every 24 hours forces these flows into an incredibly organized structure. The Coriolis effect, the same force that dictates the rotation of hurricanes on the surface, imposes a powerful constraint on the fluid motion in the core. It organizes the rising and sinking plumes into vast, twisting columns, aligned parallel to the Earth's axis of rotation. These columns, thousands of kilometers long, spiral through the liquid outer core like the threads of a gigantic screw, winding and twisting the magnetic field lines that are frozen into the highly conductive fluid. This is the final, beautiful piece of the puzzle, the feedback loop that sustains the field. The moving, conductive fluid drags the existing, weak magnetic field lines along with it, stretching and twisting them. This motion induces electrical currents within the fluid itself, and according to the fundamental laws of electromagnetism, these moving electric currents in turn generate a stronger magnetic field. This newly amplified field then gets folded back into the flow, only to be stretched and twisted further, creating a self-reinforcing cycle. The Coriolis organized columns are the key to this amplification, providing the precise helical motion needed to consistently generate a magnetic field that is predominantly dipolar, with a clear north and south pole. It is a perfect cosmic feedback loop, where motion creates magnetism, and that magnetism in turn influences the motion. A delicate dance between fluid dynamics and electromagnetism that has been perfectly balanced for eons, generating the protective shield that has quietly, faithfully, guarded our world since the dawn of life. For generations, the search for life beyond our solar system has been guided by one foundational principle: the habitable zone. This is the so-called Goldilocks zone around a star, the narrow orbital band where conditions are just right, not too hot, not too cold, for a planet to potentially host liquid water on its surface. Find an Earth-sized planet orbiting within this zone, and you've found a prime candidate for a living world. But this classic definition, while a vital starting point, is facing a dramatic revision. Astronomers are now realizing that a planet's address is only part of the story. To truly be a sanctuary for life, a world needs more than just the right temperature. It needs a guardian, a planetary force field. It needs a magnetic field. The reason for this becomes tragically clear when we look at our own celestial neighborhood. Mars sits squarely within our Sun's habitable zone, and overwhelming evidence tells us it was once a warm, wet world with rivers, lakes, and a thick atmosphere. It met every classic criterion for life. Yet today, it is a barren, frozen desert. The pivotal difference between the fate of Mars and the continued life on Earth was the persistence of our planet's magnetic dynamo. When Mars lost its global magnetic field, it lost its shield, leaving its atmosphere utterly exposed to the solar wind. Over hundreds of millions of years, this relentless assault stripped the planet bare, molecule by molecule, until its climate collapsed entirely. This is the powerful lesson from our rusty neighbor. A planet can be in the perfect spot and still be rendered utterly lifeless by the relentless fury of its star. This understanding is revolutionizing how we assess the thousands of exoplanets we've discovered. An exoplanet orbiting in its star's habitable zone might have the right temperature for liquid water, but if it lacks a magnetic field, that water would likely be unstable or lost entirely. The parent star constantly emits a stream of charged particles, a stellar wind, that batters any orbiting planets. For a world without a magnetosphere, this wind doesn't just cause beautiful auroras, it directly sputters the atmosphere away. High-energy particles from the star smash into atmospheric molecules, giving them enough energy to escape the planet's gravity. This is a slow but inexorable process, a cosmic leak that, over billions of years, can drain a world of its air, its pressure, and its ability to hold onto liquid water. A planet might start its life as a blue marble, but without its magnetic shield, it can be slowly sandblasted into a barren rock. This makes the search for a second Earth far more complex and fascinating. It's no longer enough to just find a planet at the right distance. We now need to find a way to detect signs of a magnetic field from light years away. While we cannot yet directly image an exoplanet's magnetosphere, astronomers are devising clever methods to infer its presence. One promising technique involves watching for signs of star-planet interaction. A planet with a strong magnetic field will push back against the stellar wind, creating a large, protective bubble. When this magnetosphere interacts with the star's own magnetic field, it can generate bright, detectable signals like radio emissions or specific patterns of ultraviolet light. Another method involves studying the atmosphere of the exoplanet itself. If we observe a world that is rapidly losing its atmosphere, with a giant plume of hydrogen and oxygen being dragged away by its star, it could be a telling sign that its magnetic defenses are down, that it is suffering the same atmospheric erosion that doomed Mars. This new layer of analysis forces us to see stars not just as gentle sources of warmth, but as dominant forces that shape the destiny of their planets. A star's temperament is now a critical part of the habitability equation. A calm, older M-dwarf star might offer a wider, more stable habitable zone, but a young, tempestuous red dwarf is prone to furious flares and powerful stellar winds that would bombard any nearby planet. For a world orbiting such a violent star, a powerful magnetic field isn't just an advantage, it is an absolute necessity for survival. It would be the only thing standing between a potential biosphere and a sterilizing torrent of radiation and particles. The magnetic field thus becomes the great negotiator between a planet and its star, the essential mediator that determines whether a promising orbit translates into a true home. As we continue our search for life in the cosmos, we are learning that the true marker of a living world may not be the water on its surface, but the invisible, protective force that silently holds that water and that world together. But this vital magnetic shield that has protected Earth for so long is not a constant, unchanging force. It is a dynamic and at times unpredictable system, and right now, it is behaving in ways that have scientists watching closely. We are living through a period of significant magnetic transformation, a time when our planet's protective cloak is not only weakening but also shifting in ways that feel almost alive. The most visible sign of this change is the restless wander of the magnetic North Pole. For centuries, its location was relatively stable, allowing navigators to rely on their compasses. But in recent decades, it has broken into a sprint, moving from the Canadian Arctic towards Siberia at an accelerating pace, forcing the world's geomagnetism experts to update the official world magnetic model more frequently than ever before. This isn't just a minor adjustment. It's a clear signal that powerful, deep Earth currents are reshaping the fundamental architecture of our magnetic field. This movement is part of a much larger trend, a widespread weakening of the planet's magnetic intensity. Data from satellites like the European Space Agency's Swarm mission have revealed that over the last 200 years, the field's overall strength has diminished by about 9% on average. But this weakening is not uniform. A vast region stretching from South Africa to South America, known as the South Atlantic Anomaly, has seen a particularly dramatic dip. Here, the field is now over 30% weaker than expected. This isn't just a date, a point on a graph. It has real-world consequences. In this region, our protective shield is so thin that satellites and spacecraft in low Earth orbit are bombarded with higher levels of radiation from the Van Allen belts, leading to increased glitches, temporary shutdowns, and a higher risk of permanent damage to sensitive electronics. It's a stark reminder that our technological infrastructure is deeply dependent on the stability of this invisible force. These modern changes are small tremors compared to the cataclysm recorded in the geologic record, the geomagnetic reversal. Throughout Earth's history, the North and South magnetic poles have completely swapped places. This isn't a rare event. It's a recurring feature of our planet's life, happening hundreds of times over billions of years. The evidence for this is locked in the volcanic rock of the ocean floor. As magma erupts from mid-ocean ridges and cools to form new crust, tiny magnetic minerals within the rock align themselves with the prevailing magnetic field, freezing that direction in time like a billion tiny compasses. As the seafloor spreads, it creates a symmetrical striped pattern on either side of the ridge, a continuous tape recording of Earth's magnetic history, with each stripe representing a period of normal polarity or reversed polarity. This record tells us that reversals are not periodic. They occur at irregular intervals, sometimes separated by millions of years of stability, other times happening in a more rapid succession. The last full reversal, known as the Brun-Smatayama reversal, occurred about 780,000 years ago, leading some scientists to speculate that we might be overdue for another flip. But what would a reversal actually look and feel like? The process is not a swift, instantaneous switch. From start to finish, a full polarity flip is thought to take between 1,000 and 10,000 years. During this extended transition, the dipole field we know, the simple north-south bar magnet structure, would break down into a far more complex and chaotic state. Instead of two strong poles, we might see multiple weaker magnetic poles popping up all over the globe. A compass, rather than pointing decisively north, might spin erratically or point towards a magnetic pole over Australia or Brazil. This would be a navigational nightmare for migratory animals and a significant challenge for human technology that relies on precise magnetic positioning. Crucially, however, the magnetic field would not vanish entirely. It would just become weaker and far more complicated. The most significant consequence of this weakened, multipolar field would be its reduced ability to deflect charged particles from the Sun and cosmic rays from deep space. The higher radiation levels reaching the upper atmosphere could lead to a dramatic increase in spectacular auroral displays, visible at much lower latitudes than normal. The northern lights might be regularly seen over Rome and Miami. But this beautiful side effect comes with a serious cost. The increased radiation bombardment could damage or destroy satellite constellations that form the backbone of global communications, GPS, and weather forecasting. It could also pose an increased health risk for astronauts and even passengers and crew on high-altitude polar flights. There is no evidence in the fossil record that past reversals caused mass extinctions, as Earth's atmosphere provides a robust secondary layer of protection against all but the most energetic particles. Life on the surface would likely be safe, but the infrastructure of our modern, technologically dependent civilization would face its greatest ever environmental test. The ongoing changes we see today may or may not be the preamble to the next great flip, but they serve as a powerful reminder that our planet is a dynamic, evolving system, and its invisible magnetic heart has a rhythm all its own. From the churning dynamo in Earth's core to the star-quaking fury of distant magnetars, this journey has revealed a universe woven through with invisible threads of force. We've seen how magnetic fields are not merely passive features of the cosmos, but are active, dynamic architects, shaping reality at every conceivable scale. They guide the birth of stars within colossal clouds, orchestrate the assembly of planets in turbulent disks, and carve out protective bubbles that make life possible. They accelerate particles to nearly the speed of light, paint the skies with auroras, and launch jets of matter that stretch for millions of light years from supermassive black holes. This force, born from the motion of charged particles, is a universal language of attraction and repulsion that has dictated the structure and evolution of everything we see and everything we cannot. Understanding this hidden force is truly key to understanding the universe itself. It is the bridge between the immensely large and the infinitesimally small, connecting the chaotic motion of electrons to the grand rotation of galaxies. It is the great moderator, the protector, the accelerator, and the sculptor. To comprehend magnetism is to pull back a curtain on the cosmos, revealing the intricate mechanisms that operate behind the breathtaking visuals of nebulae and galaxies. It allows us to read the history of our solar system in the magnetic fingerprints locked in ancient rocks, to predict the storms that erupt from our sun, and to even speculate on the potential for life on distant exoplanets. This exploration changes our perspective, teaching us to look for the unseen forces that are actively at work, tirelessly molding the cosmos into the magnificent and dynamic tapestry it is today. This incredible journey through 30 ways magnetic fields shape the cosmos is just the beginning. The universe is still brimming with mysteries waiting to be unraveled. So we want to hear from you. Which of these cosmic magnetic phenomena amazed you the most? Was it the perfect symmetry of Saturn's field, the tragic story of Mars, or the sheer destructive power of a magnetar's starquake? Share your thoughts in the comments below. If you enjoyed this deep dive into the forces that sculpt our universe, make sure to subscribe and hit the bell so you don't miss our next exploration into the great mysteries of space.